In the previous day, we have seen that by applying Colruy's law, we can determine the limiting molar conductivity or conductivity at infinite dilution for weak electrolytes. And that way we have done also. We have seen that we have calculated the limiting molar conductivity of acetic acid indirectly by from this equation and also we have found similarly we can calculate the limiting molar conductivity of weak bases also. Okay. So similarly we can calculate others. Now first application was determination of limiting molar conductivity of weak electrolytes. Okay. So that we have done. Then the second was determination of degree of dissociation of weak electrolytes. Okay, that we call it alpha. Now see, what is degree of dissociation? Degree of dissociation is number of ions present in the solution. Divided by total number of ions supposed to be present in the solution. I can give you a live example. See here. In this group, I think 22 or 23 students are there. I do not know. I also forgot. Now, for weak electrolyte at infinite dilution, 100% ions are supposed to be there. And this is what? This is the number of ions present at a certain concentration that we have done. Okay? So what I can write now here? Lambda MC. C is the concentration. It is molar conductivity at certain concentration. What is the concentration? C. See, it may be say 10 to the power -2 or 10 to the power -3 or -4 molar. And in that case, all the molecules do not break down into ions. But what is lambda m0? Lambda m0 is nothing but limiting, okay, I'll write here, molar conductivity at infinite dilution. That is, in this condition, all the ions are supposed to be dissociate. Okay, suppose I have taken 100 molecule of acetic acid, maybe that at certain concentration, 20 of them has dissociated. So conductivity will be shown by the ions which just come out of 20 molecules. But at infinite dilution, 100 molecules of acetic acid will break down to give you 100 acetate ion and 100 H plus ion. So what I can write now, therefore, lambda is equal to, okay, no, so alpha is equal to lambda MC divided by lambda. So from here we can calculate the degree of dissociation. Whatever the degree, whatever the value we'll get, we have to express in percentage. That is, whatever the value you are going to get, you have to multiply it by 100. Because degree of dissociation always is being expressed in percentage. Degree of dissociation. Please do the numerical. Huh? Dissociation. These numericals are very easy. Is always expressed in percentage. Whatever the value that you are going to get, it will be alpha into 100. So please write down. Third one is third application is the determination of equilibrium constant of with electrolytes. It is K. Okay, so how do you do it? See, suppose I have taken here acetic acid. So it has dissociated to give you, this means what? Please remember, unequal sign, the equilibrium sign means what? This molecule dissociate less into ions, but remain more in the form of molecules. This plus H plus. What is K? This do you know? Okay. Wait. K is equal to CH3 CO minus NH plus divided by CH3 COOH. Okay. So let alpha be the degree of dissociation. See here. Moment I put this acetic acid in water, it does not break down into ions. So if C is the concentration, okay, I'll write here. Yet T is equal to 0 second. 0 second. You will find if C is the concentration, there will not be any ion. Because it takes time. Because acetic acid molecule is having covalent bond between oxygen and hydrogen. It takes time to break it. Even if I give you a small thread, and if I tell you to tear it, it will require some time for you to break this thread. Now at equilibrium, what is the degree of dissociation? Alpha. So concentration at equilibrium will be C1 minus alpha. And how many you will get here? You will get here C alpha and C alpha. This I have explained to you in equilibrium chapter. So now I put this value here. So what should I write now here? K is equal to C alpha divided by C1 minus alpha. All right. So C and C get cancelled. So therefore K is equal to what? K is equal to alpha square 1 minus alpha. But we already know what is alpha. We know alpha is equal to lambda mc divided by lambda mg. So therefore K is equal to C alpha mc divided by lambda m0. That you know, because this one you can calculate, this also you can calculate. Square minus 1 lambda mc divided by lambda m0. So that we can also calculate the equilibrium constant. Do. Now we have read about the theory. So in your book, these theories are written after the application. How come? If you don't know the theory, then how will you understand the application? Huh? So somehow I did not like the presentation. So the portion which is given in between your unit, I have done the beginning. So I'm again telling you. Let me again. Electrochemistry is not difficult, but it has to be understood. So what is electrochemistry? It is a subject in which we study the conversion of electrical energy into chemical energy and the chemical energy into electrical energy. All right. So after that, we know that electricity can be conducted by metals with different degree of their conductivity. All metals do not conduct to the same extent because we have found it depends upon the nature of the metal. It depends upon the valence electron of the metal. It depends upon the density of the metal, And finally, it also depends upon the temperature where you find the metallic conduction or electronic conduction is inversely proportional to temperature. All right. So metallic conductivity you are going to study in physics. So initially we know that all solid substances do not conduct electricity. The substances which can conduct electricity, we call them as conductor. Substances which do not conduct electricity, we call them as insulator. And there are some very few substances which conduct electricity only when you heat them. They are known as semiconductors. So when the electricity travels through a metal, we find that any type of flow subject to some obstruction, and that is called resistance. So initially we are being given the concept of resistance by Ohm. He has mentioned that the resistance of flow of electrical energy or electricity is directly proportional to the length of the wire and inversely proportional to the cross section of the wire. Okay? And from there we came to know, from that equation you have found there is a proportionality constant. So where you write R is equal to rho L by A. L is the length of the wire and A is the cross section of the wire. So what you say about the rho? Rho is the degree of, is a constant of proportionality known as resistivity, or we call it specific resistance. We are going to say specific resistance only under the condition that length of the wire is 1 centimeter and the cross section of the wire is 1 centimeter square. If it is not, then rho will call resistivity. Then you find that if resistance is the obstruction of flow of the electricity, then it is not necessary that everywhere some obstruction will be there. There can be free flow of electricity also. All right. See, in that case, very interesting example I can give you. Meghalaya is a land of waterfalls. When the water comes up to the tip of the waterfalls, then its flow is being obstructed by so many boulders on the way of the river. But when it starts flowing down from the height, there's nothing to obstruct that water. All right? So similarly, when the electricity can flow without any obstruction, or we can ease of conductivity, okay? That is, so ease of flow of electricity, that term is called conductivity. All right? And we find that conductivity is inversely proportional to the resistivity. And on that basis, we have seen an equation, we have found that we use the symbol G as the conductivity. So we find G is equal to kappa into G star. G star is nothing but L by A, which we call it as cell constant. Now, as a chemist, I'm not going to touch the subject of physics. I know there are some substances, chemical compound also can conduct electricity. So those chemical compounds which can conduct electricity either in the molten state or in the aqueous solution, we call them as electrolyte. Clear? Now again we find all of them do not carry electricity to the same extent. On the basis of that, electrolytes are being classified into two categories: strong electrolyte and weak electrolyte. What is a strong electrolyte? Strong electrolyte are those which undergoes 100% dissociation at any concentration. It is concentrated or dilute. and weak electrolytes which undergoes partial dissociation. Okay. Now, how do you study the conductivity of a electrolytic solution or a molten electrolyte? What do you do? We simply go for mimicry of the L by A concept. So we put two electrodes. Size is 1 centimeter square is equal to the S square of our metallic conductor. And we keep it at a distance of 1 centimeter square. So the length or that length to travel their ions is only 1 centimeter. All right. So we say conductivity is nothing but the amount of electricity conducted by or carried by the ions when they are placed between two electrodes of 1 centimeter square and at a distance of 1 centimeter. So this you call it conductivity or specific conductance. All right. But in chemistry, when you make a solution, there is some way to make it because you have to express the concentration. So concentration, where this term that we are going to take is a molar solution. Molar solution, you know how to prepare. We dissolve 1 mole of a substance in 1 liter of the solution. So if I have to measure the molar conductivity of an electrolytic solution, then I must create a cell. But the cell that we have initially made, it can only hold 1 ml or 1 centimeter of the solution. So in that case, how to measure it? Anyway, we can define it. Definition can be based on imagination also. We say it is the amount of electricity conducted by 1 molar solution. All right, this is the simple definition. But if you want to exactly follow the definition of the conductivity, in that case, I have to mention the description of the cell. So what should I say? It is the amount of electricity conducted by 1 molar solution of an electrolyte which is placed between 2 electrodes at a distance of 1 centimeter. But the surface area of the electrode will be sufficient enough to hold the entire volume of the solution. Anyway, we cannot make it because our electrodes are made of metal and we cannot stretch them. So what do you do? In that case, we'll measure for 1 and multiply it. So what do you have seen there? There you have found that lambda m equal to kappa into. We know volume is always inversely proportional to the concentration of the solution. If the concentration of the solution is being expressed with molar, the molar solution, then I have already showed you that it is equal to kappa into 1000 into m. That also I have already explained you in detail. Now we are going to, because initially we have started, so we have to learn something more about the electrolyte. What did you do? We started diluting it. So we want to see the effect of dilution. So irrespective of strong and weak electrolytes. So when we started diluting electrolytic solution, we have found in both the cases the conductivity kappa, this one, it decreases. Now you know why. Because our initial cell volume is 1 ml. You have already filled up with the solution. To that, if you pour water, then the solution will overflow. When the solution overflows, from there many ions also goes out. Because of that, you find the conductivity falls. Then what will be the effect on the molar conductivity? We find interestingly the molar conductivity increases. But immediately we could find the reason, because as the conductivity decreases, volume of the solution increases by many fold. In that case, as it is a product of both of them, in this case we find the molar conductivity is going to increase. Okay, so now we have first experiment we have done. effect of dilution. Then after that, we want to see individually what will be the change of the molar conductivity of a strong as well as weak electrolytes. So when we started diluting the strong electrolytes, we find strong electrolyte, no, generally what happens is dissociation is 100% at the very beginning. So we find when you dilute it, then in that case you find the molar conductivity of the strong electrolyte increases. Then in that case, it created some interest within us. We thought that we'll go on diluting and we'll see up to what extent it will reach the maximum. So when we started diluting it, we find the graph is increasing. Then we thought if you can dilute it to infinity, this is imagination, practically you're going to do it because we know the conductivity has been always measured by some electrical equipments. So what we have done, in that case, we plotted this graph, and after that, we plotted the graph with the molar conductivity versus the square root of the concentration. We have found that it started gradually increasing. Then with the help of a scale, we extrapolated and moved at the intercept that we get in the molar conductivity, we find it is constant. All right. So whatever we have done theoretically, we found this to be correct. And we have mentioned that this is the limiting molar conductivity or molar conductivity at infinite dilution, because beyond that this is the last value where you will find the conductivity will not reach further. Because of that, we say limiting molar conductivity. And limiting molar conductivity we can get from the experiment and by extrapolating the graph. Then we went for the weak electrolytes. When we started diluting the weak electrolytes, initially there is a slight increase in the conductivity. Then after that we found suddenly a steep rise is being observed and the graph started running parallel to the conductivity axis. Then we could understand that it is not possible for us to calculate the molar conductivity of weak electrolytes as infinite dilution from the graph. Okay. Then by this time, another law has come up. We have found, we call it Kohlrausch law. Kohlrausch law says in simple and plain language that the molar conductivity of weak electrolytes at infinite dilution, molar conductivity of electrolytes, irrespective of strong and weak, molar conductivity of electrolytes is nothing but the sum of the conductivity of all the ions which is present there. And on that basis, we got an equation. We say that lambda m0 is equal to mu plus lambda plus 0 and mu minus lambda minus 0. So this is the molar conductivity of cation and anion, and these are the number of cations and anions present per formula, not per mole, per formula of the electrolyte. All right. Then we found that the proposition or the equation which is being given by Kohlrausch, it can be utilized to calculate the molar conductivity of weak electrolytes. So this equation already have shown that we find any weak electrolyte, irrespective whether it is salt or it is an acid or a base, we can calculate indirectly by the help of Kohlrausch law. Second, we have found that we can also calculate the degree of dissociation of weak electrolytes, and also we can calculate the equilibrium constant of the weak electrolytes. So this is the theoretical backup. Now we will start moving towards the practical part of it. Okay. So now there are two types of cell that you are going to use in our electrochemistry. One you call it electrolytic cell, and second one we call it galvanic cell. But very interesting here, in your book, they have mentioned this one as electrochemical cell. So I have some objection, but anyway, I have to follow your textbook. Electrochemical cell. You know, both of them are actually electrochemical cells. Okay, so we'll write here. Now, what is the electrolytic cell? Right now, it is a device in which non-spontaneous redox reactions are carried. I'll write here non-spontaneous means what? Thermodynamics, you know, no? Delta G is equal to what? Positive. Positive. It is a device in which non-spontaneous redox reactions are carried out by passing electricity. That is, you can say, in this step, we are going to study the conversion of electrical energy into chemical energy. It is the substance electrolyte that you are going to take, it will undergo decomposition. And that process is known as electrolysis. Okay? We'll write now, we'll write here, the process is known as electrolysis. So how to define electrolysis? I think all of you know. Okay, electrolysis. This you have done in school, I know, irrespective of MBOS or ICSE or CBSE. What is electrolysis? The chemical decomposition of electrolytes by the passage of electric current is called electrolysis. So please write. Where do we carry out? The device in which we carry out, that is called electrolytic cell. So what is the electrolytic cell? Cell. It is the vessel in which electrolysis of electrolytes are carried out now. It is made of insulators. Such as glass or plastic. Okay. Now I'll draw it. This thing all you know. See here. So it will have two electrodes. Two electrodes. All right. See here. Always remember, by convention, cathode should be on the right, and anode should be on the left. All right. Two electrodes are dipped in the molten or aqueous solution of electrolyte. Cathode is kept negative electrode. Is placed at right and anode positive electrode at the left. See, this is the electrolyte. So this is what? Why do you call it cathode? Because cations go to this electrode. If the cation or ions will always go to the oppositely charged electrode. So if the cations go, it has to be negative. Negative electrode, and this is the positive electrode. Now see what will happen here. So this will be connected to, and this will be the emitter. You know how much amount of electricity you have passed in ampere, or you can put a voltmeter also. You can find out the potential difference between them. Now, the anion will go to the anode and it will deposit one electron or two electrons. And that electron will travel all the way to the circuit and will come to the cathode, where the cations are going to accept it. So loss of electron is called what? When the electrons are lost, what is going to happen? So here we will find it will undergo, anions are going to lose electron, so it will undergo here oxidation. And cations are going to gain the electron. What will undergo? It will happen. You will find here it will have reduction. So what we will come to right now here? Anions migrate to anode and deposit electron. What do we write now here? Oxidation. The electrons, it will be 1 or 2 or more. So I put S in the bracket. Will travel through the metallic wire. Can I wrap this portion? Top portion?
Yes, sir.
Okay. And reach cathode, where the cations will accept the electrons and get reduced. So we have mentioned now it is a redox reaction. See here, in this one, without using any oxidizing and reducing agent, just by passage of electricity, we are carrying out a non-spontaneous, which generally do not occur by itself, non-spontaneous reaction by taking the help of electricity. Okay, so now I'll do one example. It is, we are going to do electrolysis of molten NaCl. We did not add water. So what will happen now? The moment you melt, it will undergo dissociation Na plus and Cl minus. Then all the Na plus will go here and Cl minus will come here. See, there's another convention is there. It's very funny. Huh? Why we call it funny? Because here we, by convention, we say cathode is on the right and anode is on the left. It's simply by convention. And here, when you write the equation, cathode will be on the left and anode will be on the right. So first you have to write whether you write left or right or top and bottom, first you have to write the reaction of cathode followed by anode. Okay. Cathode. Why do you give preference to cathode, this one? Cathode first, because it is in the right. So what I'm going to write here? See, cathode who travel? Na plus. I did not write anything now. I'll tell you why. Because this convention has no sense. Anode में क्या गया? Chloride has come. This chloride is having one extra electron that of the chlorine. It is octet. So it is going to lose that electron. You become chlorine atom and this electron. This is the electron which will travel all the way here. All right. Now sodium is waiting for the electron. What you are going to get here? You get sodium metal. We know we have to write one more step. Why? Because chlorine atom is not stable. So what I will write now here? Cl plus Cl is equal to Cl2. You know Cl2 is a gas. I'll write like this. Now the question is that why did I write cathode first by convention? Nothing, because it is positive and that is negative. But I will always write this one first. See, if you are hungry, you go and sit in the dining table. Okay, if your mother does not cook, can you eat? So who is providing the food to the sodium ion? Obviously the electron. Where it is being generated? A node. So I will first write this equation, then I will write this equation. See here, what has happened? Why do you say it is a redox reaction? Because chloride is losing electron, oxidation. Sodium is gaining electron, reduction. So in that case, what is going to happen? If you pass continuously this electricity to the molten sodium chloride, a time will come, all the sodium chloride will decompose to give you sodium and chlorine. So because of that, we say it is a non-spontaneous, because sodium chloride, if you melt it and keep it for your whole life, sodium chloride will remain as molten sodium chloride, will never give you sodium and chlorine. All right? Because it is not thermodynamically favorable, because the delta G is positive. So we made it favorable by passing electricity. Because of that, we call it, it is a non-spontaneous redox reaction achieved by passing electricity through them. So, all right. So what you are going to write here? What does it happen here? Oxidation. And what happens here? Reduction. See, reduction. Then I want to talk a little bit more on electrodes also. Huh? Let me please finish it. Now, electrodes. Classification of electrodes. See, electrodes are of two types. Now, what do you know? What is electrode? Which conduct electricity? Okay. Now, there are one is called inert electrode. Inert. Example: platinum. Platinum or iridium, like that. Huh? Iridium as such we do not use because iridium is very costly. So we use platinum. Now, what is in an electrode? I'll write here. These electrodes do not take part in the reaction, but simply conducts electricity. That is, it remains neutral there. All right. It will simply pass the electron. Whether the ion will take electron or will not take electron is a duty of the ion. Okay. See, just like that, when you are being served with food at home by your mother, if you do not eat, she will come and tell why you are not eating. But if you go to a hotel and order food, the person who will bring the food, he will give it to you. Whether you eat or not, he will never ask you. Second, we call it active electrode. Okay. Example, we have plenty. We can have copper, silver, gold, aluminium, iron. Oh, most of them are like this. So what should I write now? These electrodes take part in the chemical reaction. I'll not write chemical. In the electrolytic reaction. In the electrolytic reaction. Here we can write this one also, but graphite in some cases they are here, other most of the time they do not write graphite, etc. Graphite is not carbon, huh? Graphite is a allotrope of carbon. That we'll do another about this active and passive electrode. Or we call it inert electrodes. Please do inert, or please, I have sometimes I forgot also, or passive electrode. Inert or passive electrode. So I'll do the electrolysis of copper sulfate. Electrolysis of aqueous solution of copper sulfate. I don't know whether you have done it or not, but in ICSE it is there. So I'm not going to name who is in from ICSE. So right now here, using platinum electrode. Okay, see here. Copper sulfate aqueous. It will dissociate to give us copper 2 ions and sulfate ions. Along with that, we also know right from our class 11 that water also undergoes ionization. So it will be H plus aqueous and OH minus aqueous. Now see, it's very interesting. When you carry out the electrolysis, you have 2 cations and 2 anions. All right. So in that case, which anion is going to lose electron and which cation is going to get electron? Okay. So that we'll discuss later on. So anyway, the process in which more energy is required, obviously that will not participate. Any chemical reaction or any physical method, always will try to go to that side where the energy requirement is less. Okay. So now I'll write here cathode and I'll write here anode. See, both the sulfate and hydroxide will move towards the anode. Out of the sulfate and hydroxide, we find the energy requirement for decomposition of hydroxide is less than that of sulfate. So this is going to lose electron. So I'll write now here 4OH minus. It will give you 2H2O plus O2 plus 4 electron. What has happened? Oxidation has taken place. See, electron is just lost. Now this electron will travel from anode up to the cathode. Who is waiting there? Copper is waiting there and H plus is waiting there. It will find, very interestingly, most of the cases metal H plus takes, but in case of copper, copper is going to take. Okay. So in that case, you'll find Cu2 plus will take, see how many electrons is required? 2 electrons. But how many are there? 4. So I'll write now here 4 electron, 2. And that way you get here copper solid. Now I don't know how many of you have seen copper sulfate. Copper sulfate solution is pale blue. As the electrolysis continues, the pale blue color of the solution fades and ultimately become colorless. It's not magic. See here, why this blue color? Blue color because of copper ion. Gradually what has happened? The ion has become solid copper, so it will precipitate or it will deposit on the surface of the cathode. So when all the copper ion, as gradually the concentration of copper ion will decrease, blue color also will fade. And all the copper, when it is being precipitated, solution become colorless. Okay. Finish. Then I'll do the second one. Now, we'll go for using active electrodes. Using copper electrode. That is what? Active electrode. There we have written using platinum electrode, within bracket you write passive electrode. Is in first step you write passive electrode. So this one I'm going to draw. This is, I'll take here. This is also made of copper and look here, side. This is a thick one. Okay. This is also made of copper. This is cathode and this is anode. What do we have here now? Copper sulfate. CuSO4. And this equation is there. All right. So now what is going to happen here? Cathode, and here is anode. See, when I have taken active electrode, in first case, what did you find? Who gave the electron? Electron has been given by the decomposition of hydroxide. But when you take copper as an electrode, in that case, you will find because the energy to lose electron will become from copper. See here. This copper is going to lose 2 electron, right here solid, and will be 2. So here the electron is not being given by hydroxide. The electron is given by this. And what will happen now? This electron will travel to this electrode. Okay? And copper ion is going there. In that case, what is going to happen? This is going to take the 2 electron and you get here copper. So what is going to happen? See, when the electrolysis is going on, it was thick and just very thin. You'll find this your electrode has, okay, I'll write here. See, now it has become so thin because it has already gone. And in that case, what has happened? Now this has become thick because all the copper has now deposited here. Okay, now see a very interesting thing. Initially, this is the copper ion from the solution has gone here. For each copper ion, this copper has given 1 ion in the solution. So the concentration of copper ion in the solution will always remain constant. Every copper which goes into solution as copper ion, 1 copper ion from the solution gets deposited. So the concentration of copper ion never changes. So the solution is not going to change its color. Okay? The copper sulfate, the color of the electrolytic solution will not change. Why? This is because for each copper to ion getting converted to copper metal at cathode, anode liberates copper ion in the solution. Therefore, the concentration of copper to ions in the solution remains constant.